Hello, this time we're going to expand on the idea of the span of a set of vectors. So, to begin with this discussion, I'm going to start with just two vectors like this ones 1, 2, 0 and 3, 0, 0. Vectors in R3, just indicating that I have three entries, all of them real numbers. Now, what I want to do now is to collect all linear combinations of this. But what would that mean? Well, in other words, we want vectors of the form x, y, and z, of course, with three entries, right? All of them real. Just like that. For some real numbers, a and b. So we want to form, though we want to collect all the vectors that come as a linear combination of these two. Linear combination in this sense. Multiply the vectors by some coefficient, real coefficient, add them up, look up at the result, and put it in the collection. Right? Now, for example, the vector 7, 2, 0 is such a vector. And you may ask, why? Well, we see that I can write 7, 2, 0 as 1 times 1, 2, 0 plus 2 times 3, 0, 0. And this is what we need. We found A and B such that when you combine them linearly with the vectors, you get the one that you need. If we put it in symbols, right? If we think of this as a U, and this is a V1, and this is a V2, we found A and B such that U is equal to AV1 plus A plus B V2. Now, on the other hand, because we need to compare, right? The vector 0, 0, 1 is not a vector of this form. Now, how do we know? Why? Well, suppose that there are A and B real such that 0, 0, 1 is equal to A times 1, 2, 0 plus B times 3, 0, 0. Of course, this induces a system of linear equations. What is that system? Well, it is this A plus 3B equal to 0 and 2A plus 0B equal to 0 and, well, 0A plus 0B equal to 1. But look at this last equation that says that 0 is equal to 1. What we have is an inconsistent system. We arrived at a contradiction. A contradiction on what? A contradiction on the assumption that there are such numbers A and B that make this happen. Okay, so what this is saying is that now we have a suggested method to decide whether a vector is a linear combination of others. But now all that we need to do is to turn the problem of belonging to the span of a set of vectors into a problem of a system of linear equations, and then perform reductions, identify consistencies, so and so on. Okay, so what do we have? All of this motivates the following definition. Let V1, V2, Vk be vectors in Rn, meaning column vectors with n real entries. The span of V1, V2, Vk, denoted by SP of the set V1, V2, Vk, is the following collection. Is the set of all those column vectors with n real entries, such that there are k real numbers, A1, A2, AK. They may be equal, they may be different, right? They may be all zero, such that A1, V1 plus A2, V2 plus blah, 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 plus AK, Vk is equal to X. In other words, the span of a set of vectors consists of the collection of all possible linear combinations of these vectors. In our example, what we have is that the vector 7, 2, 0 is in the span of the vectors 1, 2, 0, comma, 3, 0, 0, while the vector 0, 0, 1 is not. And as we have just said, we have an effective method for deciding whether a vector is or is not in the span of a given set of vectors. With this, we finish. Take care.